In this module, we will be learning about Faraday's law of electromagnetism. Faraday conducted 3 experiments, from which he concluded that an EMF is induced in a coil when the magnetic flux cutting across the coil changes with time. In the first experiment, Faraday observed that the relative motion between a magnet and a coil changes with the magnetic flux across the coil. This change in magnetic flux with time induces an EMF in the coil. Similarly, in the second experiment, he observed that the relative motion between the 2 coils, one carrying a current, changes the magnetic flux across the coils. This change in the magnetic flux with time induces an EMF in the other coil. In his third experiment with 2 coils, he found that if the tap key is pressed, the current in coil 2 and the resulting magnetic field rises from 0 to maximum value in a short time. This results in a change in the magnetic flux with time across coil 1, inducing an EMF in it. If the key is kept pressed, there is a steady magnetic field across coil 1. Thereby, there is no EMF induced in it and the current drops to 0. When the tap key is released, the current in coil 2 decreases from a maximum value to 0 in a short time, resulting in the magnetic flux across coil 1 to drop suddenly, thereby inducing an EMF in it. From the observations of these 3 experiments, Faraday concluded that the time rate of change of magnetic flux through a closed coil induces an EMF through it, and stated the Faraday's law of electromagnetic induction. The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the coil. Let us now put this law in the form of a mathematical equation. E is equal to minus d phi b divided by dt. Let this be equation A. In this equation, E is the induced EMF. The negative sign indicates the direction of EMF and hence the current in the closed loop. When n number of turns are closely wound to form the coil, the change of flux with time for each coil is the same, and we can write for the total induced EMF as E is equal to minus n into d phi b divided by dt. Let this be equation B. In this equation, E is the total induced EMF. The negative sign indicates the direction of EMF and hence the current in the closed loop. Therefore, the total induced EMF can be increased by increasing the number of turns, n, of the coil.